Hello everyone, welcome to this video. My name is Anderson Ahrari. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to calculate soil moisture using Landsat images in the Google Earth Engine platform. Let's go to the Earth Engine code editor environment. In the first step, we need to draw region of interest through the drawing tools available here. For example, using drawing tools available here or rectangle, I'm selecting the region in the southwest of Iran. No matter which region you are selecting for, actually the main thing is that the data and the algorithm, all of them are global, and you can use this tutorial for all around the world, and it is not restricted whether in algorithm or data for a specific region. So, and then to have a focus on the selected region, use map.center object at first, helping you whenever code runs, you will have focus on the study area that is selected by drawing tools available here. And through the satellites, you can see that various land covers, water bodies, farmlands, barelands, and also the urban areas available in this region. For the soil moisture estimation, in the next steps, I will show you how to mask some of the extra classes from the soil moisture maps, such as water body and urban area, using land cover data available in the Earth Engine. So, in the next step, we need to call Landsat surface reflectance and surface temperature data. Hopefully, through the search places and dataset, all Landsat data available corrected geometrically, radiometrically, and atmospherically. So in this tutorial, I'm going to use Landsat 8 collection 2 level 2. Collection 2 level 2 is a kind of collection Landsat images that is ready to use for the surface temperature and also the surface reflectance values. Collection 2 level 2 Landsat 8 tier 1. Import it into code automatically, and here you will see an image collection for Landsat 8 collection 2 level 2. So in the next step, make a new variable, or we can call this session for Landsat collection data. So a new variable here, for example, this is Landsat equals to assign the imported image collection to Landsat variable, and then bound your data to the selected region, because Landsat has a framing structure, and also it is necessary to use filter bounds for. And then through the dot filter bounds, I'm using geometry to bound the Landsat images to a specific region. And then through the dot filter date, as you can see, you can select a specific time span for your processing. For example, I'm gonna calculate the soil moisture from 2020 to 2022. Here the starting date is 2020 and the ending date is 2022. For 2 years, I'm gonna calculate the soil moisture values. So in the next step, we need to set some filters to remove the cloudy images, and also to select only those frames covering the whole of region. So through the filter less than filter, Earth Engine filter less than, you can call those of Landsat images in which cloud cover is less than, for example, 10%. I want to use clear images for this process. So here the cloud cover is a property in the Landsat data that ranges from 0 to 100. I want to call those of Landsat images in which cloud cover is less than 10%, just like that. So then through the print, you can see how many Landsat images available according to the bounding, filter date, and also the cloud cover. 121 elements available here, and all of them listed under an image collection, and 19 bands available for each date. So as you can see here in the properties, you can see the cloud cover is less than 10%, meaning that we have almost a cloud free image. And also maybe their selected region covering different passes and rows. If you want to see how many passes or how many rows or how many images with the unique pass and rows available for this region or code and existed here, now through a print function I can see that Landsat.aggregate array, I want to see all the WRS pass values that are unique. Dot distinct actually helping us to see the unique WRS pass and unique rows. Copy and paste it or write it again for the rows this time. Landsat.aggregate array WRS rows or row is correct, and then dot distinct, meaning that just show the unique values. Run the code. Immediately you can see two passes and two rows or two types of frames available for this region. And if you want to see and if you want to show which one completely cover your study area, the simplest way is to go to the Earth Explorer website. So the Earth Explorer website launched by NASA and USGS together, and it is the main hub that releasing Landsat images. So here, through the search criteria, first of all, you can select your region of the interest. The region of the interest should be exactly the same region you have been selected in the Earth Engine platform. For example, my region is here, or let me check it again. Yes, it is near to Ahvaz, southwest of Iran. Here, Ahvaz, you can see this city in the image. So, for example, this is my region of interest, and then through the dataset, choose Landsat 8 or one of the Landsat missions that helping you to find appropriate pass and rows. Then, through the result, you will see all the existing image from Landsat for region, and you can select that image that fully covered your study area. As you can see, two types of frame is available. You can select one of them or both of them or even both of them for your processing. But I prefer to have focus on one frame because for two frames we need to do some sort of further analysis such as mosaicing that is beyond of this tutorial. So as you can see, this is my target frame that is past 165 and rows equals to 38. Back to the code and make a new filter for pass and rows. That filter again, but this time an equal filter helping us. The WRS pass equals to 165, and then dot filter Earth Engine dot filter again dot equal WRS rows or row equals to 38. Yes, back to the code again, 38 for rows, and now remove the extra codes and run the code again. Code is running and only 31 image according to this pass and row available with the cloud cover less than 10% from 2000 to 2022. In the next step, we need to calculate, or we want to start calculation of soil moisture according to the TOTRAM algorithm. The reference I'm using for the TOTRAM algorithm is this paper that you can see is available in the remote sensing of that is published in the remote sensing of environment and is available in the Elsevier or Science Direct website. So in the TOTRAM algorithm, according to the relationship between the LST and NDVI, we will be able to calculate the soil moisture through the following equations available here. This is the equation for the soil moisture that you can see. Two main parameters are NDVI and LST, and the other factors or parameters calculated based on the relationship between LST and NDVI that I'm gonna show you how to do this process in the Earth Engine platform. Although the other algorithm, such as TOTRAM, is also available, it is based on the NDVI and SWIR, but here I'm gonna use LST and NDVI to calculate the soil moisture because this thermal infrared region highly sensitive to the moisture content in the soil and vegetation covers and helping us to get accurate estimation about the soil moisture values. So this is the reference. In the next step, I'm going to show you how to do this process. In the first step, we need to calculate the NDVI and LST for the region of interest. So now make a new variable, for example, parameters. In there, I'm going to calculate NDVI and LST from 31 elements available for Landsat images. So here, a parameters equals to get all Landsat images and make a loop and throw a function making here we consider each input image or each element as an img, and in the body part I'm gonna show you how to calculate the NDVI and LST. It's very simple and easy to use. And for the first step, we need to make a variable multispectral equals to selecting multispectral, this variable, selecting the multispectral bands starting with SRB. If you go to the data descriptions, the descriptions is a comprehensive descriptions about the Landsat collection to level 2. In the bands information, you can see this product is available with 30-meter spatial resolution and available since 2013, and the bands listed here. The surface reflectance bands starting with SR, and also you can see in different wavelengths with a scale and a specific scale and factor we can use them. These data atmospherically and radiometrically corrected and no need to do further processing unless some scale and factor that mentioned should be applied on each available bands. So close the data description. I'm gonna select all the bands starting with surface reflectance B, no matter band 1, 2, 3, and then for each band selected here, I'm gonna apply a scale and a factor through the multiply and add. It is a linear equation that helping us to convert from the integer values to the original values for the surface reflectance. The multiply including the scale value and the offset is minus 0.2. Copy and paste the scale value and the offset is minus 0.2, just like that. And after correction of surface reflectance bands, now we can use multispectral band to calculate the NDVI, Normalized Difference Vegetation Index, the most popular and most applicable spectral index in the remote sensing, helping us to get information about the density and health condition of vegetation cover. That is very helpful when and applicable. NDVI equals to from corrected multispectral images dot normalized difference, helping us to calculate the normalization relationship between near infrared band SR band 5 and SR band 4. The relationship between band number 5 and 4 in the normalization process helping us to highlight vegetation cover under NDVI logic. So then rename the output band as NDVI. The NDVI image is ready, and for the next step, I'm gonna calculate the LST. A few years ago, if you needed LST or land surface temperature using Landsat images, you had to do lots of processing steps, even in Google Earth Engine platform. But now everything is changed, and thanks to Landsat Collection 2 Level 2, the surface temperature band is available, or it is land surface temperature, and no need to do any further processing. And you can download and get it from Collection 2 product and use it in the next step also for the modeling to get more information. And you don't need to deal with the LST calculation anymore, at least for the modeling process and also for estimating the land surface temperature. You can use this ready-to-use product. So the next variable equals to named as LST equals to, now from each input image we need to select the land surface temperature bands. Go to the bands information, and here you can see the land surface temperature ST band number 10 is available according to the Kelvin unit, and also there is a scale and factor value. So ST band number 10 should be selected here through the dot select, and then through a linear equation using dot multiply and add, you will be able to apply the scale and factor for the thermal band. So you can see the scale value is like that, copy and paste it, and the offset is 149. Copy and paste the multiply and add is 149, and dot rename the output as the LST or land surface temperature. And the parameters variable is going to calculate the NDVI and LST. So the function returning two images, NDVI and LST together, through the Earth engine.image.cat, I'm gonna make a stack layer from NDVI and LSTs calculated for each date with the properties of input images through the dot copy properties img.property names. So in the next step, use the print parameters to see if the processing completed or not. So the line 21 got error. Parameters, there is something wrong in the name, and now we have 31 elements, 31 image. In each date, one NDVI and one LST is available. So back to the algorithm. NDVI and LST calculated, two main factors for the soil moisture. In the next step, we want to know that how we can estimate the main parameters, the factors such as ID, IW, SD, and SW from the NDVI and LST relationship. As you can see, there is an inverse relationship between LST and NDVI values. When NDVI value increases, meaning that the amount of vegetation in the region of interest increases. Because of the moisture content in the NDVI, the LST decreases with increasing NDVI. That's why there is a negative relationship. And when the NDVI reduces in the area or the region of interest, because of the lower moisture content, after removing vegetation cover, we will have higher land surface temperature. But this logic is true, or this reason only is true for the NDVI from 0 to 1. For example, for the water areas, there is no this idea doesn't make sense. It totally makes sense for the vegetation cover and also the bare land. That's why we have the full cover and also the bare soil. So according this relationship, we have two edge, dry edge and wet edge. So, and to calculate the differences between dry edge from the full cover to the bare land, we need to estimate the wet vegetation and also dry vegetation here, the wet vegetation and dry vegetation, and also the dry soil and also the wet soil. For example, these pixels accumulate the pixels locating in this part of plot in the LST and NDVI relationship. All of them are base soil. Why? Because their NDVI value is totally close to the zero. Those of NDVI values close to zero showing the bare lands. So those of bare lands including higher temperature showing drier bare lands, because if there is moisture in the bare lands, the LSD reduces. But those of bare lands with the higher moisture provided lower land surface temperature. And the same logic we have for the NDVI. The higher NDVI values with the higher LSD, meaning that this is a dry vegetation cover, and in the vegetation cover, those of vegetation covers with the lower temperature showing the moisture, showing that there is moisture content in that vegetation cover. So accordingly, we will have some parameters such as wet vegetation and dry vegetation, dry soil, and dry vegetation that through the NDVI and LST relationship, we can calculate them in the Earth Engine platform with the simplest way. So here in the next step, I'm gonna make a new variable, for example, wet vegetation equals to, so in the parameters, get parameters dots. So in the parameters, make a new function here, each input image considered as an IMG. The parameters already included NDVI and LST for each date, and now I can select the value for this part of relationship, the wet vegetation covers. These are vegetation covers, and this point is the full cover vegetation cover with the sorry, but this is because of the higher temperature for this region. This is the dry vegetation, and this part is the wet vegetation. So here, just make a new variable. Oh, sorry, I made some mistake in the calculation. This is not wet vegetation. Actually, this is LST for the full cover. Sorry, I made some mistake in the explanation because it's a little tricky when you want to calculate this in the tutorial, during a tutorial. Actually, in this part, we want to select the LST values for the full cover pixels. That's what I'm going to do in this part. So LST full cover equals to parameters.map, make a new variable. This is the NDVI threshold or NDVI threshold for full cover. NDVI full equals to, from each input images available in the parameters, select the NDVI and select those of pixels greater than 0.3. These are full cover vegetation, vegetations that they have value number 1. This is a binary image, the full cover vegetation labeled with 1, and the lower values labeled with 0. This is a kind of mask that should be applied on actually the LST values. Then to have LST values only for NDVIs greater than 0.3, make a new variable for as LST full cover equals to get LST from each input images, and then through the update mask I will be able to only mask out all the LST values for non-full covers for the pixels less than 0.3. So I'm doing update mask according to the NDVI full, and the function returning, finally, the function returning LST for full covers with the properties of input images. Dot copy properties img dot property names. So that's what we did. In this part, we calculated all the LST values, or estimated all the LST values for vegetation covers greater than 0.3, this region. So next, I'm gonna repeat this process for the other sides of the relationship in the bare land, the vegetation covers between 0 and 0.3. So now make a new LST bare land, a new variable, but this time I'm gonna calculate the LST just for the bare lands. Parameters get parameters because including NDVI and LST through the map, make a new function, each input image consider it as an img, and then make a new threshold according to the NDVI for the bare lands equals to, from each input image, select the NDVI and select those of pixels less than 0.3. But as I'm going to select only the bare land, it would be better to select the values between 0 and 0.2, because 0.2 and 0.3 mostly covered by the, for example, some sort of vegetation covers such as rangeland with a lower density, but I want to have the bare lands exposure regions. So the values greater than equal 0, that's and then select the values img.select from the NDVI that is less than 0.2. These are the bare lands, and also most of the time these actually this range of values from 0 to 0.1 or 0.2 labeled as the bare land or various sparse vegetation cover may be included in the 0.2. So that's the NDVI bare land range, and now we need to mask all the full covers from the LST images. And now LST bare land equals to, from input image, first select the LST band here. So select the LST band, and then through the update mask, remove all the vegetation covers and only keep the bare land values for the LST. Through the mask is created. And finally, the function returning LST bare land with the properties of input images. Let me to correct the problem in writing bare land and NDVI bare land here. So img dot property names. So now print the LST full cover to be sure that the calculation is correct. And as you can see, parameters is wrong, something missed here. LST full cover and LST for bare land calculated, and also we have no problem here. So after two sides of the relationship, bare soils and full cover calculated, now we can estimate these parts or these sides in the NDVI and LST relationship. For example, this side showing the full vegetation covers with higher moisture, this corner named as the wet vegetation. So now I'm making a new variable, a VW, meaning wet vegetation, or vegetation wet, equals to, now from the LST full cover, as I calculate the I'm going to find the wet vegetation, I need to select the full cover image, and the LST for the full cover image. LST for full cover image, LST full cover. So if I get the minimum value in this image or in the time series first and the minimum of the whole images, this corner will be calculated. Full cover dot mean calculates the minimum value in each pixels, and then the minimum image is created, and I want to get the minimum value in the whole of region through this equation. Dot mean dot reduce region helping us to get the minimum value in the whole of image. The region, the reducer first. The reducer equals to Earth Engine dot reducer dot minimum value, and the geometry will be the geometry equals to the geometry or region of interest, and scale should be equals to 30. But most of the time when we are working with Landsat images, if we set 30 for the scale, most of the time we face with the user memory limit exceeded or some kind of problems. That's why I prefer to set 100 for the scale. Then to convert the dictionary, the output from the reduced region will be a dictionary. To convert it from a dictionary to a value, use that values and get it from the first item. So in order to convert it to a number, finally use Earth Engine number to be sure about the number structure for the output. That's the value, the wet vegetation, showing the minimum value of LST for the full vegetation cover, this corner. So in the next step, I want to find another corner. In the full cover vegetation, I need to get the maximum LST during the time span and get the maximum value in the whole region through this equation. So as you can see, I'm making a new parameters. This is dry vegetation. Vegetation D equals to the same actually function used for the dry vegetation with a little change. And previously we used the minimum value during a time, but now as I'm getting the dry vegetation, they have higher values in the corner. They must have the maximum value during the time, and for the whole region I'm gonna select the maximum value for the region with 100 scale values. That's how we calculate the VW and VD. So in the next step, for the Barelands, I'm gonna calculate the ID and IW, the Bareland, the LSD values for the dry Bareland, and LSD values for the for the wet Barelands. So IW, make a new variable, IW equals to, again, Earth Engine number, but this time instead of LST full cover, we are moving to another side of this relationship that is calculated through the LST Bareland. LST Bareland, all the LST values for the Bareland. If I want, because I want to get the wet values for the LST, the minimum of LST Bareland during the time calculated, and then to get the minimum value in the whole region, I'm gonna use the reduced region. The reducer here will be Earth Engine reducer minimum value, and the region of interest is geometry equals to the geometry, and the scale should be equals to 100, and then use the dot values and get the first item to convert it to a number, actually to convert it from a dictionary, the output from a dictionary to a number. And to get the LST value for the dry bare land, this part ID, we need to get the maximum with the same functions and also same parameters and arguments, and only the minimum turned to the maximum values. So as you can see, the VW, VD, IW and ID is calculated. In the next part, I need to calculate the differences between the dry bare land and dry vegetation cover. This is a subtraction between ID and VD. So, and a new variable is SD equals to a subtraction between ID and VD. The next variable is SW, the subtraction between wet bare soil and wet vegetation cover. So SW equals to IW dot subtract from VW. So SD and SW is also calculated. And now back to the algorithm. As you can see, IW, ID, SD and SW with LST and NDVI is calculated, and now we can calculate or write this equation in the Earth Engine platform easily without any problem. So I'm making a new soil moisture equation, SM, or soil moisture equals to get parameters image dot map. Here through a function I'm gonna calculate the soil moisture for all 31 elements available under this collection. Each input image considered as an IMG like this, and then in the body of function we can write the equation. The equation equals to get from each input image and then calculate the equation through the expression function. So here we have a numerator and denominator with two separate parentheses. So as you can see, first in the numerator part, ID plus SD, just like that, ID plus SD multiply NDVI, subtract from LST. That's the numerator, and denominator is like that, IW minus IW subtract from ID subtract from IW plus the subtraction between SD and SW plus the subtraction between SD and SW, and multiply to NDVI in the denominator. So here we have some all the variables in the expression are unknown, and we need to set each variable to their consistent and also to their match variable in the code that we have been created before. So starting with ID equals to the ID that is already calculated, SD equals to the SD variable already calculated, the NDVI already calculated and available in each time from the parameters. The parameters here from the input IMG that I'm selecting the NDVI. The only thing that's changing in this equation is the NDVI and LST in each date. The constant values, all of them calculated through a time series data, and the only thing changes in this equation is NDVI and LST, and by the changing NDVI and LST we will have a new soil moisture image for each date. So, and the next is the LST. It is also available in the parameters from each input image. Select the LST image and ID already assigned, but the IW missed here. IW equals to IW with the same name And the next one is SW. SW equals to SW, and the layer name could be soil moisture with TOTRAM algorithm. So the function finally returning the equation with the properties of input images, img.property names, just like that. So as you can see, soil moisture is calculated. If you want to see the result, if you want to see if any syntax error happened in the code or not, you can print the soil moisture. After a few moments, in the right panel, you will see the image collection that is calculated or not. It is still under computing. But I think there is no syntax problem, because if there is any syntax error in the code, immediately a kind of error returning in the console. 31 elements again is available, but this time for each date there is one soil moisture images with a specific range of values. So now I want to plot the range of NDVI values. Actually, I want to get the range of soil moisture value for the selected region. But in order through the user interface chart image.series, just like that. Instead of image collection, we will have the soil moisture, and instead of the region, we will have geometry. Instead of the reducer, as I'm gonna get the average of soil moisture, reducer.mean, and the scale better to equals to 100, and instead of x property, we need to import the property explaining the time of the acquisition date in each image, that is system time start. That is very important parameters for the time series analysis in the Google Earth Engine platform. System time start, and now the code again is running. A new chart is under generating, but in order to avoid some noises in the soil moisture values, would be better to mask out the urban areas and also the water bodies. It is simply you can simply do it in the Earth Engine platform, and also there is no problem here. You can see the soil moisture value calculated in the wet seasons and also the wet months in the autumn and also in the winter. We have higher soil moisture, and also in the drier months such as the summer we have lower soil moisture. And if you want to see the visual characteristic, let me to mask out the water cover and also the urban area, and after then I will show you how you can visualize the result. So to mask out the urban areas and also the urban areas and also the water bodies, we need to make a mask layer here. The mask equals to fortunately in the search places and dataset, or in the Earth Engine database, the dynamic word product is available. In the previous tutorials in my YouTube channel, I showed you how we can use dynamic word product to map the land cover with 10-meter spatial resolution for the region of interest. And now again I'm using this product that is highly accurate in the global format. I'm using this product with 10-meter spatial resolution to mask out the urban and also the water bodies. So this is an image collection number 2. First I'm gonna filter it based on the region of interest through the filter bound, bounding the land cover map to a region I'm working, and then I'm going to make a mode image to find the frequent classes in my study area through the .mode, and then the target band should be label band. As if you go to the data description in the Google Dynamics, you can see it has 10-meter spatial resolution, and one band is labeled with containing different classes. Class number 6 is built, and also class number 0 is water. These are target bands or target classes, and I want to mask them out from the calculated soil moisture data. So I need to select class number 0 and class number 6. So in the mode map that is created from the label band, so in the next step, I want to select those of value that are equals to 0, or those of pixels equals to number 6. And then in order to set the class for water, I want to set 0 for water and urban area, and set number 1 to the other pixels in this image. I'm using knots that helping me to change the values in the images, or make an inverse relationship here. For example, when I'm using a map.addLayer for the mask, I'm gonna show you here better. Clip it based on the region of interest, no need to visualization, and just name is mask and use the false. For example, when I'm selecting pixels with value 0 and number 6, you will see that the produced mask that clip based on the geometry. You will see that the mask layer that is created have two values. It is a binary image that's showing number 1 for the urban areas and also for the water bodies. I'm waiting for the results. Yes, it is loading now, or under visualization process. It is a binary image. All the pixels I think something is wrong. I'm running the code again. This is the mask image. I'm gonna increase the contrast. After new range of value applied to the mask, I got apply and see the final results. But only we have one class, showing that definitely something is wrong. So here, for example, I'm gonna make a new, I prefer to make a new variable for the mask layer to avoid such kind of errors. This is the land cover, and mask layer equals to, from land cover, select those of pixels equals to, for example, a number 0. So when the code is running, you can see that all the water areas, all the pixels for the water class showing value number 1, and the rest of classes showing the 0 actually. And then I'm waiting for the visualization process. Yes, now you can see that all the waters included with number 1 and the rest of classes have the number 0. And we can set a new condition here to select class number 0, or LC dot equals to class number 6. And now you will see the urban and water pixels with value number 1. The mask is creating, and you can see that the urban structures added with value number 1. And now through the dot knot, I can make an inverse binary image that set the 0 value for the white region and the one value or the value number 1 for the black pixels. So run the code again, and you can see that I changed the order of binary image through that nuts. And after the new image or the new mask is created and prepared, in the next step, I'm gonna apply the mask on the calculated soil moisture images. You can see now the binary image showing value 0 for the water and urban area and value number 1 for the rest of pixels. To apply this in all soil moisture images, now make a new variable soil moisture mask equals to, or masked soil moisture equals to, get soil moisture images, and then through the map make a new function, or there is a simple way to mask instead of making a new loop, you can make a stack layer just like that, and then through the update mask, apply the mask layers on all bands available in the soil moisture data set. It's simpler, I think. So then through the map.add layer, I will be able to see the result, soil moisture masked, clipped based on the region of the interest, and then I left the visualization parameters empty. Soil moisture masked is visualizing, and use the false at the end to avoid automatic visualization process. So run the code again, and final masked layer is available in the layer setting, but after calculation is done, you can load the masked layer here. Until then, here I'm gonna show you how to get export from the soil moisture mask. It is very simple. Just export that image to drive, and here I'm click on the masked soil moisture layer here, then back to the code until the layer is visualized completely. I'm gonna show you how to get export from export.image to drive. The first argument is image equals to soil moisture masked here, and then that should be clipped based on the region of interest before, and the description, the name of output equals to soil moisture, and scale should be 30 meter for the region of interest, and the region of interest is the geometry here, and then a CRS or a spatial resolution. I'm gonna use the original coordinate system that is available in the mask layer through the .crs, and then the maximum pixels in each frame should be 1E13, and the folder you want to save the result is equals to, for example, the folder name should be anything. You can make a new folder with soil moisture name that's result saved there. And to avoid some possible errors in the calculation in the saving process, use .float to convert some integer values to the float format to make a integrated or consistent format for the output values. So now through the layer settings, you can select each band here available in this stack and visualize it separately, or you can run your code and download it through the task layers. You can save it first into the Google Drive, and after file is saved in the Google Drive, you will be able to download it from there and open it up into the some desktop softwares you are working, such as For example, yeah, this is the soil such as ArcGIS Pro or anything else. This is one of the images, and then through the 90% stretch, I'm increasing the range, the rate, the contrast or visualization characteristic. And after enhancement process is done and the new range of values created, click on apply to see the final result visually. So yes, there is. I'm clicking on apply, check the mask layer on, and after applied image visualized, you can see the visual characteristic. And also this is a binary, this is the grayscale image, darker region, lower values, lower soil moisture, and brighter regions, higher values, showing the higher soil moisture values. So as you can see, for example, the croplands in this image showing higher moisture content, that totally makes sense. And also the darker regions have lower moisture, that is according to our expectations. So I hope you liked this tutorial, and I hope this could be useful in your own projects. If you had any question or problem regarding to this tutorial, you can put your comments in my YouTube channel, and also you can find this tutorial code below this video in my YouTube page actually, and then you can compare your own code with mine. And also if the problem still exists, you can reach me out through there, and I will try to help you to do your own projects. Thank you for your attention.